Today we're going to talk about an aspect of light that we often refer to as color. In physics, we define color as the wavelength of light. On average, for humans, the wavelength is between 380 to 740 nanometers. This is the spectrum that most humans see, and it is the rainbow that you're familiar with. When we talk about particular colors of photons, we have to mention the exact number of nanometers that their wavelength is. A red laser pointer, for example, has a wavelength of 633 nanometers. Now this is a HeNe laser because helium and neon are used to make the red light. Another important color is the hydrogen alpha line. This is one of the primary colors we use to identify hydrogen in the universe. And it's going to have a wavelength of 656.3 nanometers. A green laser pointer, on the other hand, is going to have a different wavelength. That's approximately 532 nanometers. Notice that the green light has a smaller wavelength, but it's more energetic, so it's going towards the blue end of the spectrum. Of course, humans don't talk about nanometers when we talk about colors. This is because of the photoreceptors in the back of our eye, which are in the rods and cones, detect different wavelengths at different amounts. Notice as this graph, the sensitivity of green and yellow are at a peak, whereas blue is much lower. So this tells us that humans have very poor blue vision compared to our green and yellow vision. Keep in mind that this graph represents an average. Some humans, their green is not as high of a peak, their yellow may not be as wide, or the blue might even be higher. So the range that is the color spectrum is going to be slightly different for each person. This variance is different than being colorblind. When you're colorblind, and there are multiple types of colorblindness that people can have, you may not have one of the sensors at all and you completely miss it, or your mind might be interpreting a color, say red, as yellow. Regardless of the human, everybody would see the same wavelength of light. What changes is how it's absorbed and how the brain interprets it. So in one sense, everybody sees the exact same color, and in another, everybody sees a different color unique to themselves. For example, a wavelength of 610 nanometers, I might interpret it as orange, but your eye might interpret it as more of a reddish orange. Same wavelength, but different interpretation of what we call the color. Next, we're going to focus on how humans in general interpret different colors. When humans see the color black, they're actually not seeing any light at all, so it's no color. White, on the other hand, is when your eye sees all the colors at once, it interprets it as white light. Sometimes the colors aren't even, and you'll end up with a white light that's slightly bluer or slightly redder. But for the most part, white is all the colors combined. For all the other colors, it gets a little more complicated. Here we have a color diagram to help simplify the matter. There are three primary colors: blue, red, and green. When two of the primary colors combine, the light we see is a secondary color. For example, red plus blue gives us magenta. Combining blue light with green light gives us cyan light. And what is probably most surprising at all, red light plus green light produces a yellow light. You'll notice that if we add all the blue and all the red and all the green, we get white. The same happens if we add all the secondary colors, magenta, cyan, and yellow. We get white light. By combining different colors at different intensities, or how bright they are, we can get all the different colors in the spectrum. One other term to know is complementary colors. These are any two colors that are on opposite sides of the diagram. So yellow and blue, red and cyan, green and magenta. Because complementary colors include a primary and the opposite secondary, when you add them up, you always get white. I'll save adding up color examples and how mixed paint works for another video.